All right, folks, we're going to move on to our next lesson here, which is secure data plane operation. Now, this is going to be quite an extensive discussion here because we're talking about securing the IPSec tunnels that happen between the vEdge devices for our service VPNs to be able to communicate with each other. So we're going to talk about what the operational IPSec components are in the data plane. We're going to look at how we verify IPSec data plane connections. We're going to describe the operation of the bidirectional forwarding detection feature within the secure data plane, how traffic gets segmented in this network by using VPNs or layer 2 or layer 3 segmentation mechanisms. And then we're also going to talk about how applications are going to be recognized in the secure data plane with a very specific element that's added to the SD-WAN fabric to allow that visibility into the applications. All right, so data plane of any network is going to be responsible for handling data packets that are transported across the network. The data plane sometimes is even referred to as the forwarding plane for that reason. In a traditional network, data packets are typically sent directly over the internet or another type of public IP cloud, or they're sent over some sort of service provider managed VPN like an MPLS tunnel or something to that effect. Now, if the vEdge routers in our overlay network were to send traffic over the public cloud, that transmission typically would be considered insecure. Anybody in the middle would be able to sniff that traffic, and they would be able to implement different types of attacks, including various man-in-the-middle attacks on that traffic itself. So the underlying foundation for security in the Cisco SD-WAN data plane is the security of the control plane. Because the control plane is secure, meaning that all of our devices are validated and that control traffic is encrypted, remember, either using DTLS or TLS, we know that that information cannot be tampered with. All right. Now we can be confident in using routes and other information learned from the control plane that's going to allow us to create and maintain our secure data paths throughout the network and to our various vEdge routers. The data plane provides an infrastructure for sending data traffic among the vEdge routers in this SD-WAN overlay network. Now we know that that traffic happens between the vEdge routers. So that data plane traffic travels within a secure tunnel. And in this particular case, we're not using DTLS or TLS. We're actually using a secure internet security connection with IP security or IPSec. So unlike the control plane where we were using DTLS and TLS to secure the traffic, in the data plane, we're using IPSec to secure the traffic. So the data plane implements all of the key security components of IPSec, which would include authentication, encryption, integrity, and so on. All right, now authentication, first of all, IPSec as a suite or a protocol suite includes many different elements, right? The data traffic is going to have ESP applied to it, HMAC SHA-1, with anti-replay protection, AES 256 for encryption, and 2048-bit RSA asymmetric key exchange, and ESP for authentication. And that's what we get from the vEdge router to the vEdge router. Now, this can be very difficult to manage in a very large environment, primarily because of how we deal with the keying material and how we transfer and manage the dispersion and the allocation of the keys. But we'll talk about how that occurs in this particular case that makes it so compatible and makes it so flexible. So let's talk about the three cornerstones of this overall encryption process. The first is authentication, right? The control plane contributes to the underlying infrastructure for data plane security because it does have elements of authentication built into it. Authentication can also be enforced by two other mechanisms in this SD-WAN fabric solution. RSA, the Rivas-Shamir and Edelman encryption process with 2048-bit keys. And then we also have two standard protocols from the IPSec security suite framework, encapsulated security payload and authentication header. and those can be used to authenticate the origin of the data traffic. We also have the ability to incorporate encryption. The standard ESP protocol protects the data packets and the payload. The AH protocol protects both the payload and that non-mutable header fields, or those non-mutable header fields that we see within the header. And we're going to see a slide a little bit later on that talks about what those non-mutable headers are. The key exchange encryption is actually done using the AES 256-bit cipher. Integrity, that is a mechanism for us to guarantee that the data traffic is transmitted across the network without being tampered with, right? The data plane implements a lot of different mechanisms, and these are all, again, part of that IPSec security protocol suite. We've got the ESP protocol that encapsulates the payload of the data packets. We've got the HMAC SHA-1 algorithm, which is actually used by the IPSec AH protocol, and it combines a key hashed authentication code with a SHA-1 cryptographic process to ensure data integrity. AH is going to encapsulate all of those non-mutable fields in the outer IP header. Again, we'll see a diagram about that a little bit later on. I'll point that out again. And the payload of the data packets. So we can configure the integrity mechanisms that are supported on each of our vEdge routers. We do that through the various templates that we apply. And then this information is exchanged inside the router's TLOC properties, right? The transport location properties. So if two vEdge peers advertise different authentication types, they can actually work to negotiate the type that they want to use, and they're going to fall back or accept whatever is the strongest method. The anti-replay scheme is what protects against attacks in where the attacker is duplicating encrypted packets to try and spoof a connection so that they can look as though they're part of an overall communication process. All right? Now, when it comes to the key management, this is a huge component, right? Traditional internet key exchange is not very scalable when we're talking about traditional IPsec tunnels. So we handle this in a little bit of a different way on our vEdge devices and our SD-WAN fabric. Before a pair of vEdge routers can actually exchange data traffic, they have to establish an IPsec connection between them, which they use, this IPsec session as the secure communications channel. So the routers have to authenticate each other over this particular connection. Just like we saw with the control plane, the data plane is going to use keys to perform that individual device authentication. Now, in a traditional IPsec environment, key exchange is actually handled by another protocol called IKE, or IKE, the Internet Key Exchange Protocol. IKE actually first sets up a secure communications channel between the devices, and then it establishes a security association between each pair of those devices that they want to exchange data with. IKE uses things like Diffie-Hellman key exchange, which is an asymmetric key exchange process, so we're not actually exchanging raw key material across an unsecure link. And that allows us to kind of generate a shared secret key that allows us to further encrypt the additional IKE communication process. To establish the SAs, SAs are security associations that might exist between the pairs of devices. So to establish those SAs, each of those devices, which we will reference as just N in this particular case, because we're going to use a formula later on to describe the scalability issues with IPsec, they're going to exchange keys with every other device in the network, and they're going to generate these per pair keys, generating essentially a unique key for each remote device that's going to attach. Right? This scheme means that a fully meshed network, each device is going to have to manage powers of 2 keys, right? N to the power of 2. So if I have 20 devices in the network, we're going to have 20 to the power of 2 key exchanges and 20 minus 1 keys that we're going to have to manage. So a 1,000 node network could have 1,000,000 different key exchanges and up to 999 keys that we have to manage. So this whole point in talking about this is not the way it works in our SD-WAN fabric, but it does point out why a standard IKE-style key exchange doesn't really scale well as the network size increases. And IKE, in this particular case, could end up being the bottleneck in maintaining the network, right? There's other things that could be required, right? A handshaking is required to set up the communication. That can be resource intensive. The processing that's required for the key exchange can also take a long time, and so on. So in the Viptela Cisco SD-WAN implementation of our data plane authentication and encryption, we only establish SAs between each pair of device that we want to exchange data with. And that's kind of the same as what we were talking about before, but we get rid of the IKE process altogether. To provide a scalable solution to this data plane key exchange, we take advantage of the fact that we already have a secure DTLS control plane connection in the overlay network. We already know that that's secure. We've already established that network because that's how the devices register in the first place. Because the control plane uses authenticated, encrypted, and tamper-proof connections, there's really no need in the data plane to set up secure communication channels to do the data plane authentication. So that data plane encryption and key generation is actually done by AES 256, which is a symmetric algorithm that uses the same key to encrypt the outgoing packets and the same key that we're going to use to decrypt the incoming packets. So each vEdge router basically generates an AES key for that data plane. Specifically, we're going to generate a key per TLOC. We'll talk more about TLOCs a little bit later on, or transport locations. And we transmit these keys to the vSmart controller in our OMP route packets. Again, we'll talk about OMP a little bit later on as well. So OMP carries a bunch of information like policy information, keying material for encryption, but it also includes things like routing information. So it's very similar to a protocol that distributes IP route information. So these packets contain information that the vSmart controller is going to use to determine whatever the network topology is, including all the vEdge router's tuples of information, those transport location information, which includes the system IP address, the traffic color, and the encryption method, whether it's IPSec or GRE. But in addition, now we have that AES key. So the vSmart controller places those OMP route packets into what we call reachability advertisements that it then sends to all of the other vEdge routers in the network. That way, the AES keys for all the vEdge routers get distributed across the entire network. Even though the key exchange is symmetric, those devices use that information in kind of an asymmetric fashion. Basically, the result of this is that we have a very, very simple and scalable key exchange process that doesn't have to use per pair keys, right? The vEdge router is going to send that OMP packet, which has the system IP, the color, the encapsulation, the site ID, and the AES key to the vSmart controller. And then the vSmart controller in turn is going to forward that information to all the other vEdge routers. All right. Now, if control policies that are configured on the vSmart controller, if those policies limit the communication channels between the devices, the reachability advertisements that are actually sent by the vSmart controller contain information only for the vEdge routers that you're allowed to exchange data with. So a vEdge router might learn the keys, but it's only going to learn the keys for those particular vEdge routers that they're going to be ultimately allowed to communicate with. Now, to further strengthen the data plane authentication and encryption process, the vEdge routers regenerate their AES keys pretty aggressively. By default, it's every 24 hours. That key regeneration mechanism makes sure that no data traffic is dropped when the keys are being exchanged as well. So that's a pretty important concept. The liveliness of the security associations between the vEdge router peers, that's going to be tracked by something that we're going to talk about a little bit later on in this section, which is bidirectional forwarding direction packets. These are going to be periodically exchanged over the IPSec connection between the peers. IPSec is going to rely on that connection status to the vSmart controllers, right? So if data connectivity between the peers is lost, that means that the exchange of BFD packets stops, and that means the vSmart controller learns that the connection has been lost and the software, the SAs, are going to be timed out. Traditionally in IPSec, we do have timeout values, data lifetime timeouts, and time lifetime timeouts for traditional IPSec SAs, but in the Viptela solution, there are no explicit SA idle timeout periods. All right, that's because we rely primarily on that periodic exchange of those BFD packets between them. All right, now the frequency that the SA keys are regenerated really gets rid of the need to implement an implicit SA idle timeout, because we're essentially renegotiating this each time. All right, now from an integrity standpoint, there are many, many different elements that are integrated into the data plane protection that provide integrity. ESP, which is the standard IPSec encryption protocol, encryption and authentication essentially of the inner header, the data packet payload, and the ESP trailer. Let's take a look at the next slide and we'll kind of see what we're talking about in this particular case. Right? We can see that the encrypted piece includes the inner IP header, the data packet payload, and the ESP trailer for the packets themselves. We also have AH, which is the standard IPSec authentication protocol, and it protects with authentication the entire data packet. Right? We see that highlighted here, including the inner headers and the outer headers, the data packet payload, and the ESP trailer. Now we also have something built into this. We don't really see it documented on this slide per se. I mean, there is a bullet point, anti-replay protection. This is also part of the standard IPSec software suite. It provides a mechanism to number all the data packets to make sure that the receiving router accepts only the packets that have valid, unique numbers. And we'll talk more about how those numbers are calculated in a little bit. Now, going into a bit of a deeper dive here, the first of these components that we talked about was ESP. That's a standard IPSec encryption protocol. It protects the data packet's payload, the inner IP header fields with encryption, which occurs automatically, and authentication, which can either be enabled or disabled depending on the feature profile that you create. Now, for authentication, ESP is going to perform a checksum calculation on the data packet's payload and inner header fields, and it's going to place that resultant hash, that hash that we calculate, which is called the digest, into a 12-bit HMAC SHA-1 field at the very end of the packet. We see the ICV checksum field listed at the end. Now, what happens is, once the data is processed, if the two checksums match, the packet is accepted. Otherwise, the packet's going to be dropped. So this encapsulation, this ESP UDP encapsulation, allows us to encrypt and authenticate the inner headers, the payload, the MPLS label, if it does exist. It doesn't necessarily have to exist if we're not running MPLS, the ESP trailer field, and then we place again that HMAC SHA-1 hash in the ICV checksum field at the very end of the packet. The outer header fields, which are added by ESP and UDP, are not encrypted or authenticated in this particular process. Now, as we mentioned, the second component that contributes to the data packet integrity is AH. That is our authentication protocol that's built into IPSec, which protects all fields in the data packet with authentication. AH is going to perform a checksum process similar to that that's done by ESP, except that instead of calculating the checksum over just the payload and the inner IP fields, IP header fields I should say, it calculates it over all of the fields in the packet. That means the payload, the inner header, all of those non-mutable fields in the outer IP header, and so on. we place the HMAC SHA-1 hash into the last field of the packet as well. So just like with ESP, AH on the receiving device performs that same checksum calculation. It accepts the packet that has a matching checksum. All right, so the center stack or the kind of the middle of this diagram here represents that encapsulation that's performed by AH in combination with ESP. We see the dark blue encrypted piece. We see kind of the lighter blue authenticated piece. Again, ESP encrypts those inner headers, the payload, the MPLS label, and so on. All right. If we have situations where the data packet is authenticated, where authentication is not required for the data packet, we can disable data packet authentication altogether. That's an optional value or an optional configuration within this process. All right, data packets would then just simply be processed with ESP, which encrypts the entire original packet, but we don't see any of that authentication. So we have a couple of options. We can run ESP with UDP encapsulation, which would mean that we have encryption and authentication that's provided by ESP. We can run AH and ESP with UDP encapsulation. Now, if I run ESP with just UDP encapsulation, the outer UDP header, this box right here and this box right here, are not going to get authenticated. Only the ESP, the internal ESP header, the sequence number, MPLS label, those things are going to get authenticated, and of course the encryption is still going to be applied. What we're seeing actually on this particular diagram is a representation of everything applied. AH plus ESP plus our UDP headers. Now if I just did no authentication and just did encryption, then this outer kind of light blue box would just simply go away. We would not have any authentication applied, we would only have the encryption applied. All right? It's important to understand that the SD-WAN fabric devices exchange not only the encryption key, which is part of that symmetric encryption process, but also the authentication keys that are used to generate the HMAC SHA-1 digest. We're not just generating a generic digest without any secret sauce, if you will, because that doesn't protect us from man-in-the-middle attacks. We need to have some sort of secret keying material as part of that hashing process to make it unique that the attacker in the middle would not be able to duplicate. All right, again, both of those keys, the asymmetric encryption key and the authentication key that's used for the hashing process, are going to be distributed as part of the transport location properties for a particular vEdge router. So even though the IPSec connections where the data traffic is actually being exchanged is secured, they will travel across public network space like the internet. So it is possible for a hacker to launch a replay attack, which is typically called a man-in-the-middle attack, against those IPSec connections. In this type of attack, the attacker, is basically tampering with the data traffic by inserting a copy of the message that was previously sent by the source, meaning that was already authenticated and encrypted and so on. We didn't necessarily duplicate that message, gain access to that message or modify it in any way, just retransmitting a copy. Now, if the destination device can't distinguish that replayed message from a valid message, it may authenticate that attacker as a trusted source, and it might incorrectly grant that attacker unauthorized access to services. So the last thing we'll talk about on this slide before we move on to our next discussion is how do we mitigate this particular type of threat. So as a counter to this type of attack, the overlay network software implements the IPSec AntiReplay protection. This basically contains two components that are included. All right, both of these components protect the integrity of the data and the traffic stream. Right, the first component is associated to sequencing. Right, establishing sequence numbers, if you will, with each of the data packets. So what happens is the sender inserts a sequence number into each IPSec packet, and then the destination checks that sequence number accepting only packets with unique, non-duplicate sequence numbers. The second component in this process is what we call a sliding window, which defines the range of the sequence numbers that are current. So that sliding window has a fixed length. Maybe it's 64, so 1 to 64. Or it can adjust up and down, right? Typically up, right? The destination accepts only packets that have sequence numbers that fall within the current range of values within that sliding window. Now that doesn't mean they have to be consecutive, right? Because sometimes packets have to be retransmitted or lost. But as long as the packet that was retransmitted has a sequence number that falls within that sliding window, we're going to accept it. If it doesn't fall within that sliding window, then we're going to drop it, right? So we're only going to allow packets that fall within that sliding window. When the destination device receives a packet and the sequence number is larger than the highest number in the sliding window, it actually is going to shift that window to the right, basically changing the lower end value and changing the overall range of valid sequence numbers that are going to be accepted by the devices. This scheme is what allows us to protect against those man-in-the-middle type of attacks, because by choosing a proper window size, we can ensure that if a duplicate packet is inserted into the traffic stream, two reasons why it would probably fail. The sequence number would already be within, it could be within the current range, but it would be a duplicate, right? Or the sequence number would basically fall out of the current range because we've already moved on to a different phase in the window calculation, right? We've already slid that window over, so the old sequence numbers are no longer valid. Either way, the destination is going to drop that packet. So the sequence number combined with this sliding window helps protect against man-in-the-middle attacks, making sure that integrity of the data stream is maintained. All right? So that's a lot of information, but I think it's really important information to understand the underlying process that allows us to protect the data plane in our vEdge to vEdge communication. So there's a few commands that we can use to verify data plane IPSec connections. They're not quite the same as like a quick show crypto IPSec SA or show crypto ISAK and PSA, but very similar outputs, right, as far as what we're actually trying to validate. Three basic commands, excuse me. Show IPSec inbound connections. That would be show IPSec inbound dash connections. That's going to display the information about the IPSec tunnels that originate on remote routers, so the ones that are going to other vEdge routers. Show IPSec local dash SA. That's going to show me all my security association information for the IPSec tunnels that have been created for the local transport locations, the local TLOCs. This is also going to be on my vEdge routers as well. Here we're looking for the security parameter indices, we're looking for the SAs being established in both directions, we're looking for the encrypted and decrypted packets, we're looking for the encapsulated and de-encapsulated packets, and so on. And then we have our show IPSec outbound dash connections. That's going to show us the information about the IPSec connections to remote routers on the device. So that's going to be also on vEdge routers only. Of course, most of this applies to the vEdge routers only anyway, right? Because we're looking at data plane security in this particular case. We're not looking at control plane security. So that does make sense, all right? There's some other commands we can issue, of course. We can do a show, here's an example of a show IPSec inbound dash connections, and we can see the source IP and the source port and destination IP and destination port. We can see the transport location addresses. What is the color? In other words, the VPN that we're passing over. What is the local TLOC address and what is the local TLOC color? Basically just saying, hey, these are the tunnels, the data plane tunnels that we've established to our remote locations. All right. If I wanted to see the same thing in vManage, I would log into vManage. From the dashboard, I would navigate to Monitor on that left side of the panel, click on Network. I would choose whichever vEdge device from the list I want to look at, and in the top right corner are two little joined rectangles that show the dashboard in real time, and showing dashboard, I should say, and real time. We can check either one of those. So we'll go ahead and click real time, and then from the top left page, part of that page, we can click on the IPSec inbound connections, and we can simply scroll through and look at all of those inbound connections. All right. So the next thing we're going to talk about is a feature that's not really unique to the SD-WAN environment. We've seen this protocol implemented in many other routing protocols. Is bidirectional forwarding detection. Now, BFD is a detection protocol that's designed to provide fast forwarding path failure detection times regardless of the media, regardless of the encapsulation, regardless of the topology, regardless of whatever routing protocol that we're running, right? We want to make sure that we have a consistent failure detection method that really works across all platforms and works across all transports. Now, we have mechanisms built into different protocols like BGP and EIGRP and OSPF to detect failures. But oftentimes, those failure mechanisms are going to be based on very lengthy hello intervals and dead intervals that we use, or keep alives in the case of BGP, that we use to form adjacencies. Okay, so we want something that's kind of independent, that can provide a uniform rate, and that can also actually monitor other aspects of the link itself to be able to provide for failure detection with many different techniques, right? What happens is we establish a BFD session between two endpoints over a link, all right? If we have more than one link, we can build multiple BFD sessions between them. This actually happens automatically in the SD-WAN fabric environment, and actually cannot be disabled in the SD-WAN fabric environment. We can kind of tune the properties of BFD, but we can't disable BFD, all right? The session is established with a three-way handshake. It gets torn down the same way. We could potentially use authentication as well, either MD5 or SHA-1 authentication, but there is no automatic discovery mechanism, right? In normal routing environments, BFD sessions have to be explicitly configured between endpoints. In the SD-WAN fabric, it's enabled by default. And it allows us to identify essentially what's happening on the network. Now, there's two ways that BFD can typically run, asynchronous mode and demand mode. If we're running in asynchronous mode, both endpoints will send out periodic hellos to each other, and if a certain number of those packets aren't received, the session goes down. In demand mode, no hello packets are actually exchanged after the session is established. Basically, it's kind of assumed that all the endpoints have another way to verify connectivity to each other. So that's probably most likely not the method that we're going to use in our particular case. We're going to use the asynchronous mode. So in our particular case, BFD is going to be enabled by default. It is a path liveliness measurement. It also allows us to qualify the measurement detection protocol that runs between all of our vEdge routers in the topology. We don't run BFD on the control plane. We only run BFD on the data plane. So it detects things like the up-down state of the link, packet loss, latency, jitter. We can also see things like the IPSec tunnel MTU settings and so on. When we get into our BFD, our feature templates, we're going to take a look at the BFD feature template, and we're going to talk about what each of these settings are in one of our future lessons. So BFD actually runs directly inside of the IPSec tunnel between the vEdge routers, and it operates, like I said, in echo mode, which is kind of that asynchronous mode that I was referring to. It automatically starts when the IPSec tunnel is established, and it cannot be disabled. So we use a hello interval to establish the up and down detection process, and we use a poll interval and a multiplier for the application aware detection. Again, we'll talk about those details later on when we get into the BFD feature template. We can customize BFD by modifying a feature template. We can do this on a per color basis, or we can actually do this on a per vEdge basis, and we'll talk about that again a little bit later on. Okay? Jitter is going to be, which is kind of the delay between packets. That's going to be derived by calculating loss and latency numbers in the network. So just to talk about some of the specifics here, it is enabled by default. It is going to run on connections between vEdge routers, any tunnel that's established, any IPSec tunnel with destination and source and destination TLOCs. BFD is going to be sending those hello packets periodically. The timer is actually a 1-second timer, and again, it's used to determine whether the session is still operational. If a certain number of those hello packets are not received, and we can adjust that value, the BFD session considers that the link has failed, and that brings the BFD session down. When that BFD session goes down, any route that points to a next hop over that particular IPsec tunnel is going to get removed from our forwarding information base, and meaning that we can't use it to route, right? It might still exist in the routing information base, but it's not going to exist in the forwarding information base. Now we can modify the BFD hello packet intervals. We can modify the number of missed hello packets, which is going to be based on that BFD interval multiplier before BFD declares that a link has failed. The BFD protocol sends hello packets periodically to detect those faults, like we talked about in the previous slide, and this is again going to happen between different vEdge routers. By default, BFD sends those hello packets every 1,000 milliseconds, and if we want to change that interval, we can do this in the command line by modifying the BFD global parameters using the hello interval command, or we can do it through the adjustment of a feature template that we've applied to a particular device template. After BFD has received a certain number of hello packets on the link, or as it continues to receive those packets, if it stops receiving those packets for a certain number of time, like I said, it's going to declare that link has failed, and the number of packets is based on a multiplier of the hello packet interval time. Now the default values is 7, a multiple of 7 for the hardware vEdge routers, and 20 for the vEdge cloud software routers. Again, we can adjust these values. These are default values, but we can apply a BFD feature template to a device to modify these particular settings. All right? So if I don't receive, for example, a hello after 7 seconds on a vEdge hardware platform, I'm going to go ahead and consider that that link has failed. We can use the multiplier command in CLI if we're doing a CLI adjustment, or we can again adjust it through the use of a template. If I wanted to go in and create a template for this, this is in 16.2 and later, I can go in and manage the BFD sessions in vManage, or at least look at the BFD sessions in vManage by simply going to Monitor, going to the network screen. I'm going to locate the vEdge router using the sort options in the drop-down, or do a search, and then I'm going to scroll through the list of devices in my table. I'm going to select whichever vEdge router I want to look at by clicking on a system IP address. That's going to open up a screen, and then I can click on the real-time button in the left pane, and then from that I can see the BFD sessions. So we can see this information in vManage. Again, we will get into more details later on about how we actually manage the settings for BFD by applying different feature template settings. Now, another function within the SD-WAN fabric is the ability to do segmentation. Segmentation is really just a way to virtualize network elements within the network itself, right? It's existed forever. I mean, there's lots of different solutions that we can use to do segmentation, as to isolate traffic, as simple as maybe a VLAN. Maybe we create a layer 2 segmented network. Maybe we're doing some virtual routing and forwarding. There's a bunch of different options. But we may want to keep different lines of business as separate from, maybe for security reasons or whatever. Maybe the IT department wants to keep authenticated users separate from guest users. A retail store wants to separate video surveillance traffic from the transactional traffic. An enterprise might want to give a business partner selected access to some portions of the network, but not others. And then we have industry regulated standards like HIPAA compliance, the Health Insurance Portability and Accountability Act, or the PCI compliance, payment card industry compliance standards, and so on. All right. Viptela actually uses kind of more prevalent and scalable models for creating segments. Essentially, the segmentation in this case is done at the edge on the vEdge routers, and then that segmentation information is carried in the packets in the form of an identifier. All right, so we might have, for example, 3 vEdge routers. In this diagram, we can see Site 1, Site 2, and the data center. And we are describing essentially 3 different VPNs in this particular case. We've got the blue VPN, we've got the green VPN, and we've got the red VPN. And those VPNs can carry different prefixes and so on, and they can route different information. Some of them can be layer 2. We can see that separated with an 802.1q tag. Some of them can be layer 3. We can kind of have a mix. But because each vEdge router has an OMP connection over a TLS tunnel to the vSmart controller, it can propagate that routing information to that vSmart controller. And then on the vSmart controller, you as an administrator can enforce policies to drop routes, to change transport locations. In other words, where the overlays to the next hops. Maybe we're doing that for service chaining. We'll talk about that a little bit later on. Maybe we're doing it for the purposes of traffic engineering, or maybe just to simply change the VPN ID. Our last module will talk about policy implementation and so on. But we can apply these policies either as inbound or outbound policies within the vSmart controller. So all prefixes that belong to a single VPN are going to actually be kept in a separate routing table. This provides layer 3 isolation that's going to be required for the segments in the network. So, Site 1 has 3 different VPN routes, VPN tables, Site 2, and so on. They're each going to have multiple VPNs, VPN route tables, but they're only going to have one route table, right? Now, sorry about that. So what I was saying is that the vSmart controllers can maintain the VPN context for each prefix as well. Separate route tables provide isolation on a single node. So the question is now, how do we propagate that routing information across the network? This is actually done using VPN identifiers. A VPN ID is carried inside the packet and it identifies each VPN on the link. So when we configure a VPN on a vEdge router, the VPN has a label associated with it. The vEdge router then sends that label information along with the VPN ID to the vSmart controller. The vSmart controller then propagates this vEdge to VPN ID mapping information to the other vEdge routers in the domain. The remote vEdge routers then use this label to send traffic to the appropriate VPNs. Does that make sense? So the local vEdge routers, when they receive that data with that particular VPN ID label, they use that label to demultiplex the data traffic. Basically, it's kind of the same way that an MPLS label might be used, and it's designed kind of based on that concept. All right. We have some default VPNs that are used. We talked about those. VPN 0, which is our transport VPN that's maintained kind of internally, and then also our internally maintained VPN 512. We also have the ability to do dual stacking with IPv4 and IPv6 addresses. So segmentation is a very powerful tool in this overall architecture. Now we can see that data plane routing table. If we go into vManage and we go into monitor and network, we can select a particular device in our device groups. and then we can see the specific routing table for those particular devices. What is the VPN ID for that particular prefix? What protocol did we use to discover that prefix, whether it's a static protocol, or static prefix, I should say, a connected route, an OMP learned route, and so on. And then we see all the other details. What's the transport location IP address? What's the next hop IP? What is the transport location encapsulation? It can either be GRE or IPSec, but in most cases it's going to be IPSec. What is the TLOC color, and so on. All right, now another very powerful element within this overall SD-WAN fabric is the ability to do application recognition. So in addition to examining the network and transport layer headers in our data packet, we have centralized data policies that can be used to examine the application information in the data packet's payloads. This deep packet inspection gives us complete control about how those data packets from a specific application or a group of application families get forwarded across the network. This allows us to assign the traffic to be carried by specific tunnels. To control the traffic flow of a specific application traffic or group of traffic or a specific application itself based on things like traffic loss or latency properties on the tunnel, we need to be able to identify that traffic, and we do that with application-aware routing. DPI, or Deep Packet Inspection, requires an additional license, but it is a feature that's available in the SD-WAN devices, and we use the Cosmos QoS-MOS Deep Packet Inspection Engine, which has about 3,400 or so different applications that it can recognize. Now, Cosmos itself is kind of out of the scope of this class, but if you go out to Google and you search on Cosmos Deep Packet Inspection, again, QoS-MOS, you can read all about this application. It's kind of a third-party application that's been integrated into this platform to provide us the ability to do that deep packet inspection. All right, so why would we want to have that application awareness? We need to have that application awareness so that we can track network and path characteristics of those data plane tunnels between the vEdge routers. And then we can take that information to compute the optimal path for that data traffic based on the policies that we've established. Those characteristics that we're trying to monitor include things like packet loss, latency, jitter, the loading conditions of the links, or even potentially the cost of use of the bandwidth across a particular link. So the ability to consider the factors in this path selection process, other than those used by, say, standard routing protocols, which is typically reachability or standard metric information, link status information, and so on, gives us a whole bunch of enhancements and enhanced stability in the overall architecture. So we could say, for example, in normal operation, the path that's going to be taken by the application data traffic through a network is optimized. We have the best possible path. We're directing the traffic to the WAN link that supports all of the required elements that we've set aside in our service level agreement, which could include acceptable packet loss, acceptable latency, acceptable jitter, and so on. If we have a network failure, maybe a link goes up or down, or the performance is degraded to a certain point, the tracking of the network and those path conditions by this Cosmos application-aware routing process in real time can reveal those performance issues, and then it can automatically, based on some policy that we've configured, activate a strategy that redirects that data traffic to the best available path. So as the network recovers from those conditions, we can then fall back to the original paths that were the preferred path. Network costs can be reduced because data traffic can be more effectively load balanced and shared across multiple links. Application performance can be increased without the need to do massive or expensive WAN upgrades to the topology and so on. We already talked about the fact that each vEdge router can support up to 4 transport locations or 4 TLOCs. So that means that a single vEdge router could connect up to 4 different WAN networks. That's why it's so important to have this application awareness so that we can choose the best possible path out of a vEdge router over the service VPNs to make sure that we're taking the best possible path. All right, so that was kind of a longer section, but we talked about the data traffic between the vEdge devices is encrypted with the use of IPSec. All of the elements of IPSec, right? Our data plane integrity is maintained through the use of those IPSec tools and tool sets that we have, which include authentication, encryption, and anti-replay mechanisms. The data plane IPSec connections are monitored through either the vManage GUI interfaces or through the device's command line interface. We spent a little bit of time, not a whole lot of time, because we really can't disable this feature, so it's about really just tuning the feature, which we'll talk about more later on, but the bidirectional forwarding detection feature, which allows us to identify the liveliness of a path, to do quality measurements, to detect whether or not we're meeting the requirements for a particular path, and so on. So it's not just the up-down state, we're also monitoring things like packet loss, latency, jitter, and so on. The isolated virtual private networks are established across any transport. VPN carries traffic, which can include things like MPLS labels if we're running over an MPLS network. The routing information is exchanged through OMP. And then we talked about DPI, the Cosmos engine that allows us to do that deep packet inspection so that we can have application visibility for, thousands and thousands of different applications so that we can make sure that the service paths that we have implemented meet the requirements of those specific applications. All right, so we'll wrap up this lesson. We'll see you guys in the next lesson.